final paper of this session is a contribution from the University of Notre Dame. It's Monte Carlo simulation and FTIR studies during CO oxidation of platinum. And the authors are R. Sant and E. Wolf, and Eduardo Wolf will present the paper.
The title is different than what it appears in the book. I was able to convince the chairman to change it, but couldn't make it to the book. So we're going to be talking about a combination of theoretical simulations and some experimental work that we recently done. First, I'd like to recognize some of the previous papers on this area. Yesterday we heard a talk from the group by Sid and co-workers on absorption using infinite reaction rates to study the adsorbate phase transition. Then there is a model by Dumont and Dufour on absorption desorption with finite reaction rates. Elte has also proposed a model to explain oscillations of single crystals. And then there's a recent paper on a model in which they consider dipole-dipole interactions as well as migration on the shape of the TPR spectra. What we like to do is to look at the effect of nearest neighbors on the rate of absorption and reaction, and also compare it with some well-known models, as well as with the Langmuir-Hinshelwood rate expressions of this Monte Carlo simulation, and try to understand what they really mean, and also compare it with some infrared results. First of all, the mechanism of the reaction is well understood, and we also know the rates of the various steps. So in terms of elementary steps, we are considering absorption of CO, absorption of oxygen and dissociation, desorption of CO and oxygen will not desorb, surface reaction between absorbed species, and also we are adding migration of CO from one side to another possible pathway. These are some details on the simulation. I'll go quickly. The way to do this is to take these rates of reactions and normalize them by the sum of all the rates of reaction by this expression here. What was this? And to obtain probability. So we can, the interesting thing is that we can actually get numbers that are based on experimental work and not only simulations here. And we also can look at the effect of nearest neighbors. And these are several algorithms in which we're looking at different, this is collision probability and so on, I'll explain that later. But the fact that a molecule can land and look to the nearest neighbors and react with them if there is a site that is occupied by the same molecule or a different molecule is accounted by this factor here. Now the simulation itself is pretty simple. I will look at 100 by 100 sites, and what we do is we generate, look at a random site on the surface and look at whether it's empty or occupied. If it's occupied, we ask for reactions by comparing these probabilities with a random number that is generated from 0 and 1. If it is empty, we ask whether it can be absorbed or not, and we check for oxygen or CO absorption, and then we go back to another site, and if the site is occupied, we can go for a reaction, or we can go for desorption and migration, depending on the values of the various probability in relation to this random number. And then we go back until we cover all the sites, and that generates one MC simulation iteration, and we go through thousands of these iterations until we get some steady-state calculations. Now the problem was to try to understand what was the meaning of these calculations, and what we have done here is to compare some of the results with a sort of a landmark, and the landmark is the typical absorption desorption reaction type of isotherm that you get from Langmuir with calculations, and that is given here. And you can see here that depending on what kind of nearest neighbor interactions, you can get different results here, where we have the CO coverage here versus the rate of absorption in this case for CO, and this is a product of the rate of absorption times the concentration of CO. And so you can get different results depending on what kind of assumptions you make as to the effect of nearest neighbors. And the closest you get to the Langmuir here is to assume this particular model, which is one in which we assume a variable absorption and reaction probability, meaning that the probability of absorption and probability of reaction depends on the nearest neighbor, and then we randomize the surface after every iteration. So the Langmuir is a truly random type model as one would expect, but have in mind that you can get quite different results depending on what you assume for the other model. And didn't look too good here, but this represents an MC simulation of a surface that is initially covered by oxygen. The blue points are oxygen and the reds are CO. These are several times, and what you notice here is the aggregation of CO into domains and clusters, and these clusters start growing as you go from different iterations, and they start growing until they cover the whole surface. And this is the main difference between a simulation in which you consider a completely random choice of sites like the Langmuir and what happens in a Monte Carlo simulation where you have to consider spatial effects. And so the formation of these clusters, and finally the surface is completely covered. This is another simulation of an emission of a surface that is initially covered by oxygen, and these are two conditions. First, atmospheric pressures and lower pressure here. And what you see, what we're doing is putting CO on the gas phase. We start with the oxygen covered surface and a little bit of CO, and you see again the formation of these aggregates and the formation of larger domains here. These are steady state conditions after we have about 10,000 iterations probably. And this is what happened. The surface, you notice there are very few empty sides here, whereas at the lower pressure here, we have much, the domain of empty sides is bigger. The clusters are really dominated by oxygen, and you have a few sides here that are covered by CO. So the picture of a atmospheric pressure and the low pressure type studies is quite different in terms of the population of the surface as one would expect. Also consider migration. For example, we look at a CO covered surface, and in this case the rates are sufficiently large, so we don't need too many iterations. But and we look at how the CO is depleted from the surface as a function of number of iterations or time, and you see that depending whether we consider migration increases the rate of depletion of CO from the surface, and also depends on what kind of pressures you're using. This is the rate of oxygen absorption at two different pressures. The lower the pressure, of course, the rate in this particular case is the oxygen partial pressure. Let's see, 2.5. Oh, there. The lower the pressure, then the longer it takes for oxygen to move out of the surface. CO out. Now, this is an important thing that we've done, is to relate the size of the cluster to something that we can measure. These simulations are very nice, and you can produce very nice graphics, but we cannot actually see the surface cover, but we can see the result of the aggregation of CO clusters by changes in the wave numbers in the infrared. And so what we've done is we use some equations that consider the dipole-dipole interactions and the relation of those to the wave numbers that you would see for CO absorbed, and did the simulations, and these are the results. And we have a CO covered surface in this case, and we have various values of the rate of oxygen absorption as represented here. You can see that migration, for example, Km is migration, doesn't play any particular role at the higher pressures. It's important at the low pressure. And the other thing that you will see is during reaction, the frequency here doesn't change too much under this condition until you get to a very low coverage. And the important thing is that we can now go on and look at experiments in the literature and our own experiments and try to see if this really happens. Another effect of the formation of clusters is that the prediction, this is the number of CO molecules produced versus CO coverage. We're igniting a CO covered surface, and the predictions of maximum for a Lagrangian model will be at 0.5. What we see is that this appears a little earlier because of the formation of clusters again. Let's see, I'll jump over this one. And again, looking at the effect of an oxygen covered surface, this is the reverse type of experiments. We start with oxygen and we put CO in the gas phase, and we see in this particular type of experiment significant change in wave numbers for versus coverage in the particular experiment. And at the high pressure migration, all the curves are the same here for migration, Km, and no migration at the high pressure. So this doesn't have any effect on the wave number at high pressures. Now, I suppose this is the most important slide because it contrasts the simulations that we have done with our experimental results for ignition. And you can see that we see very little shifts in wave numbers when we are reacting CO, and which agree very well with the calculations from the MC simulations. Now, when we are dissolving CO, that is destroying the clusters, these are the MC simulations, and these are some isotopic experiments in which we have, in fact, observed a significant change in wave numbers for CO absorption, desorption. So the presence of oxygen really keeps these results in line here, and you see very little change in wave number, whereas in desorption, absorption type experiments where you are destroying clusters, and then you see the effect on the infrared. So I'd like to conclude this presentation by emphasizing that these MC simulations are pretty sensitive to the kinds of algorithm that you put in the simulations in the first place. That CO migration increases the rate of reaction if you add that to your model, and also decreases the cluster size, and this leads to a more homogeneous distribution of CO on the surface, as you would expect. And that we have a fairly decent argument, I think, given all the assumptions of these simulations, between our infrared results and the results from these NC simulations. Thank you for your attention.
Are you able to use the results from the simulation to estimate the dynamics of an ignition, just how rapidly it will occur?
Well, you can fit it, but you have to add sort of a factor there, because it is possible to relate the NC iteration time to real time, but you have to kind of scale the experiments, and that is sort of adjusting the results. So
MC calculations are very tempting, and once you start working on it, it's like eating peanuts, I've discovered. You can't stop. However,
I just started, so I don't have that
yeah,
taste.
however, we've discovered that there are several things that now become subtleties. As you've mentioned, there are the rules of the game that you don't know a priori which rules are right. You use your intuition. And then there are parameters that have to be put in. You've shown us several different rules that can be used. The parameters are presumably constants in the model that you're using.
They're our own experimental results.
Yeah, but they're constants. They're
Yes.
not spatially dependent.
They are, in the sense that they account for nearest neighbors.
Well, they do. I mean,
Yes.
I couldn't read the slides from where I was sitting, so I couldn't
Yeah,
tell.
yes, they are dependent because they account for nearest neighbors. We are assuming that we have an homogeneous surface, however, which is
Inhomogeneous.
homogeneous.
Homogeneous.
Yeah.
Right. In fact, it's inhomogeneous because then the local environment changes things like activation energies and possibly even pre-exponential factors. So the real question is, how do you know when you're doing it right?
When they
You
agree,
have measurements that are sensitive enough to discriminate.
well, when they agree with experimental results, in other words, yes, the surfaces, and there are a lot of approximations in assuming that we have an homogeneous surface and 100 by 100 type matrix represent what we have, which is a polycrystalline catalyst.
Now, the real issue is how do you know when the rules are right? Because if the rules are wrong and the parameters are okay, you can still be wrong.
No, I think as far as the rule is concerned, the effect of nearest neighbors and the formation of clusters, which is something that we can measure, and that can be measured fairly accurate. I think
How?
by infrared.
Well, that's indirect.
I mean, that's all you're going to be able to do at this point. Okay.
Okay.
So
Well, we can
we're
talk
doing the
about this
best
more.
it can be done. If you suggest another way, I'll go for it.
I don't know, your talk was on rhodium, and you talked about platinum.
Well, you were in the first
I know I was there,
talk.
but my interest is in fact in rhodium. And you've shown that the band in fact doesn't shift in platinum.
Yes.
The question is, I presume you've also done rhodium. And my question is, are you seeing the islands of rhodium, or are you following the same rules of the road as Alex was?
No, we haven't done rhodium. The reason is rhodium is a much complicated surface in the first place. Not only you have the several species, here we're looking at changes only in the linear CO. We're not adding the bridge bonded CO, which is, because we see very little of it, it's less than 0.1%.
Is it island? You know whether it's island?
Honestly, we haven't done the calculations on rhodium. Okay, so I don't know.
Thank you. I think I'd like to end the session now since we only have an hour for lunch or coffee or whatever you want. The final session starts at noon in this room, so please come back and hear.